If you're working with embedded systems, you know that making them responsive, making them react instantly to the real world is everything. And the key to that is mastering interrupts. They really are the nervous system of your microcontroller. But let's be honest, figuring out how a signal gets from a physical pin all the way to your code can feel like a black box. So today, we're going to tear that box open and demystify the entire process.
All right, here's our game plan. We're going to follow a signal step by step on its journey. We'll start with why we even need interrupts in the first place. Then we'll see how that signal gets from a pin to the external interrupt controller, the EXT. After that, we'll meet the NVIC, which is kind of like the CPU's bouncer. We'll get into the nitty-gritty of priorities, see how your handler code actually gets to run. And finally, we'll look at some of the really cool hardware magic that makes this whole thing ridiculously fast.
So, first things first. Why all this fuss about interrupts? Why can't we just, have the CPU constantly check if a button is pressed? Well, that question gets us right to the heart of a fundamental choice in embedded systems: polling versus interrupts. Think of polling, that's the guy on the left, like a kid in the back of a car asking, "Are we there yet? Are we there yet? How about now?" The CPU is stuck in this endless loop, burning power, burning clock cycles, and it can't do anything else. Plus, if it gets busy, it might actually miss the button press altogether. Now look at the interrupt approach on the right. Here, the CPU can just go to sleep. It enters a low-power mode, totally relaxed, until bam, the button press happens. That hardware event physically forces the CPU to wake up and pay attention. It's way more efficient, and it guarantees you won't miss a thing. Okay, so interrupts are the way to go, but how does the hardware actually pull this off? It all starts at a physical pin when a voltage changes. How do we tell the microcontroller, hey, this specific change on this specific pin is important? Well, that is the job of the EXTI, the External Interrupt and Event Controller. Getting this to work means talking directly to the registers, and there's a specific recipe you have to follow. First, pretty obvious, you set up the GPIO pin as an input. Second, and this is a really crucial step, you have to use the System Configuration Controller, or SYCFG, to connect that physical pin to a logical EXTI line. Third, you tell the EXTI what to watch for. Is it a rising edge, a falling edge, both? And finally, you have to unmask the line in the EXTI's interrupt mask register. You can think of this like opening a gate. If you don't unmask it, the signal is just going to hit a wall. Trust me, forgetting that last step is a classic rookie mistake. Now, here is a hardware rule that trips up so many people. That SYCFG thing, it works like a multiplexer. There's only one EXTI line for each pin number. So you have an EXTI line 0, an EXTI line 1, and so on. What this means is you can connect pin PA0 to EXT0, or you can connect pin PB0 to EXT0. But you cannot, under any circumstances, connect both of them at the same time. You have to pick one. It's a hardwired limitation. So let's say our signal made it. The EXT saw the right edge, the line was unmasked, and it sends a request forward. But it doesn't just barge right into the CPU core. Nope. It has to go through the nested, vectored interrupt controller, the NVIC. The NVIC is the real brains here. It's the gatekeeper that decides who gets to talk to the CPU.
And understanding this two-stage system is key. The EXTI is a peripheral from ST Microelectronics. Its only job is to watch the physical world, the pins, and spot an event. The NVIC, on the other hand, is a standard part of the ARM Cortex-M core itself. It has no idea what a GPIO pin is. All it sees are incoming requests, and its job is to sort them, decide which is most important, and tell the CPU which chunk of code to run.
And that brings us to the most important job of the NVIC, managing priorities. I mean, in any real system, you're going to have tons of things trying to get the CPU's attention at once. A button press, a timer overflowing, data coming in from a sensor. The NVIC has to be the traffic cop that decides who gets to go first when they all happen at the same time.
And now we get to what is probably the most counterintuitive thing about ARM interrupts. You'd think a big number would mean high priority, right? Well, it's the exact opposite. Priority 0 is the highest, most urgent priority you can have. A priority of 15 is way less important than a priority of 14. It feels completely backwards, I know, but you have to burn this into your brain. Lower number means higher priority.
And to make things just a little more fun, there's another detail. The ARM architecture allows for 8 bits of priority, which is 256 levels. But the chip manufacturer, in our case ST, gets to decide how many of those bits they actually wire up. On many STM32s, you only get 4 bits for 16 levels. In this example, it's only 3 bits, giving you just 8 levels from 0 to 7. The other bits are just ignored.
You absolutely have to check the data sheet for your specific chip, or you'll be wondering why setting a priority of 15 is acting exactly like a priority of 7. Now, to give us even more control, that priority value can actually be split into two parts, a preemption priority and a sub-priority. Preemption is the really powerful one. If an interrupt with a high preemption priority, a low number, arrives while a low priority handler is running, the hardware will literally pause the running code to handle the more urgent one. That's called nesting. The sub-priority doesn't do that. It's just a simple tiebreaker. If two interrupts with the same preemption level are waiting, the one with the lower sub-priority number gets to go first. Simple as that.
So the NVIC has made its decision. It gives the CPU the green light. At this point, everything is automatic. The hardware freezes whatever it was doing, saves all its important registers onto the stack, and then it looks up an address in a special list called the vector table. That address points directly to your code, the C function you wrote to handle the event, also known as the interrupt service routine, or ISR.
But this brings up a really practical problem. To save space and resources, chip designers often group multiple EXTI lines into a single interrupt for the NVIC. A classic example is that pins 10 through 15 all trigger the exact same function. So, when that function runs, how in the world do you know which pin was the culprit? Was it pin 10, pin 13, something else? The solution takes us back to the EXTI peripheral. Inside that shared ISR, the very first thing you need to do is check the EXTI's pending register. It'll have a bit set that tells you exactly which line fired. Once you know the source, you can run your pin-specific logic. But now for the most critical part, and I can't say this enough, you must clear that pending flag before you leave. And weirdly, you do it by writing a 1 to that bit. If you forget to do this, the interrupt will immediately fire again as soon as your ISR ends, and your CPU will be trapped in an infinite loop. It's a classic bug. Now, you might be thinking that all this register saving and restoring sounds like it would be kind of slow, but the ARM Cortex-M core has some absolutely incredible hardware optimizations built right in to make this whole process ridiculously fast. This is really the secret sauce. The first optimization is called tail chaining. So imagine a low-priority interrupt handler finishes, and the NVIC sees that another one is already waiting. A less sophisticated CPU would waste time restoring the main program's registers, only to immediately save them all again for the new interrupt. The Cortex-M is way smarter. It just skips the whole restore and save dance and jumps directly from the end of the first ISR to the start of the next one. This cuts down the latency between interrupts to just a few clock cycles. It's brilliant. And even cooler than that is late arrival. Picture this, a low-priority interrupt happens, and the CPU starts stacking its registers to get ready. But right in the middle of that process, a super urgent, high-priority interrupt comes in. The hardware is smart enough to see this happen. It finishes the current stacking operation, but then, instead of fetching the code for the low-priority handler, it grabs the handler for the high-priority one instead. It ensures the most critical task always gets handled first, with zero extra delay. So there you have it. We've traced the entire signal path and even looked at the hardware that makes it all so efficient. Let's quickly wrap up by summarizing the key points and, more importantly, the common mistakes you'll want to avoid. You know, building a good mental model also means knowing where the traps are, and these are the big 5. Forgetting to enable the clock for the SYS-CFG peripheral, trying to map, say, both PA1 and PB1 to EXTI line 1 at the same time, not unmasking the line in the EXTI register, forgetting to do the final enable in the NVIC, and of course, the big one we just talked about, not clearing the pending bit in your ISR and getting stuck in a loop. If you can remember to check these 5 things, you will solve 90% of your interrupt problems. So we've really picked apart the journey of one signal through some very deterministic, highly optimized hardware. The final thing to think about is what happens when you lay a complex piece of software on top of all this. How does this beautiful hardware system interact with something like a real-time operating system, an RTOS, that's trying to manage its own tasks and priorities? Well, that RTOS relies on this exact same hardware to do its job. Understanding this foundation is your first step to mastering those much more complex real-time systems.
If you like this one, the YouTube algorithm says you're gonna love my other videos, so go check them out.